Hello everyone, this is another video recording that I promised join for you about IGCSE 0478. Okay, so what what I have done for you? Okay, so here um I already gave or I already record first video that is called system numbers. I already record another one that is called some images and measurement. And this is the last video that I record for you that was about data transmission. Okay. So let me show you another thing here. So in this part I have all the wait a moment because I let me look here and I want to show you this part. Here I have resources, IGCSE documentation, and this one. Okay, so this is the syllabus of IGCSE that you are going to present this year, and this is the contents. Okay, so if you look at this, you have 10 chapters. Okay, so here in this part, let me show you. Let me show you here. You see resources. Um, I have one, two, three, four, five, six resources for this first six chapters. So I have to do the resources for this part. That is chapter 8, 9, and 10. Why? Because in here, in this another folder, I have the chapter 7 that is about algorithms. Okay, so this is what we're going to continue doing. And today, our topic is about hardware. And if you notice, I have three PowerPoint presentations for hardware. So let's start. Okay, so in this moment, we are going to talk about the chapter number that is about hardware. Okay, so let's start. Computer architecture. Okay, so what do we have here? When we are talking about computer architecture, is the way that the computer is made, even inside, talking about the physical parts in the computer. So, which are the physical parts that, if you want it, you can see in your computer? So, let's put here um, physical computer, computing, no, computer parts. So this is all that we have in our computers as physical. So you have the mouse, you have the keyboard, you have the screen, you have the speakers, and many other devices. But inside we have more physical parts. So let me this a small image. Let me select this one. Okay, what do we have here? Obviously the hard drive, optical drive, the RAM memory, the CPU. Oh, wait a moment because no, it's still recording my voice. The motherboard and more. Okay, so we are going to start talking about those parts. Okay, so let's talk about the first one that is called the CPU. Is the central process unit. Okay, that is the CPU. Is often called the brain of the computer. Why? Because the CPU controls everything the computer does. Okay, so what the CPU does that do? So we have fetch instructions, process the data, and control the inputs and output devices. So as always, I like always making drawings, and this is what. Let's suppose that this is the CPU And let's suppose that here we have our memory, run memory. Okay, I'm going to put these pins here. Okay, and let's suppose, for example, that here we have something that is called I/O devices. What is this? Input. And what is this? Output. Okay, so what the CPU does. So the CPU fetch information from the RAM. Fetch. So what is that? That the CPU is going to go to the RAM memory to get some information. Okay, then the CPU is going to process, the information. Okay, then the CPU is going to send the information, for example, in this case, to the output device. Could be the screen, could be a printer, could be speakers. Okay, and the input, for example, you are sending some information. Let's suppose that you have a calculator. Let's suppose that this is a calculator in the computer. So let me open it. So we open the calculator, and you are going to start using, for example, your keyboard 7 times 2. So using your input devices, the 7 is sent to any part in the RAM memory. Let me put this here. Okay. The multiplication process is going to be in another part of our RAM memory, and the number 2 is going to be in another part in of our RAM memory. So the CPU gets those information, accomplish the multiplication, and show the results. Okay, so that is what the CPU does. Okay, okay, so fetch instructions from memory. So the CPU gets the information from the memory, processes data according to those instructions. So the example that I gave you, you are going to multiply 7 times 2. So the CPU process that instruction and obviously control the input and output devices. So that means that the information is going to be shown by a screen, or maybe you have a system that talks that operation. For example, let's suppose that you have Siri, and you ask to Siri to go to do that multiplication. So Siri is going to use the speakers just for telling you what she's doing and the result of that process. Okay. And sends the result of processing to be output. That means that is going to be shown by a screen or using the speaker, or store. Why store? Because maybe you are going to say, okay, multiply 7 times 2 and store the information in the hard drive. Okay. In short, the CPU processes instructions and data that are input into the computer so that the result can be output. Okay. Okie dokie. So let's continue here. Main parts of the CPU. Okay. So in the CPU, we have something that is called ALU. We have something that is called CU. We have something that is called registers. So what is that? The ALU is the arithmetic logic unit, performs calculations and logic for maths and comparisons. So let me show you. So the ALU is the one that, for example, the same example that I gave you, the ALU is going to receive the 7 times 2 and is going to process the result. Okay, or maybe you are going to compare those numbers and you are going to say that 7 is greater than 2, or the 2 is less than 7. Okay, so math operations and logical comparisons. Okay, that is the purpose of the ALU. Now we have another one that is called the CU, that is the control unit. So the control unit directs all operations inside the CPU. So decides what happened next. So let's suppose here that you are going to, let's suppose that you have 15, this number 15, okay? And you have the 7 times 2, okay? So you know, and then you are going to compare if 15 is equals to this result, okay? So let's suppose that you put inside the computer this number, then you are going to do this operation. So the control unit is going to execute this part first. Why? Because you type 15 first. Then you are going to multiply those numbers 7 times 2. So the control unit knows that this is the second activity that the computer is going to execute. Then you are going to compare if 15 is equals to this multiplication result. Okay? So the control unit is the one that is going to see to perform the instructions and is going to give to the processor which instruction next. Okay? So that is what the control unit performs. Okay? Is the one that is going to say to the ALU, okay, ALU, you must multiply those numbers. Then you must compare those multiplication results. You are going to compare with this number. Okay? So that is what the control unit does. Okay? Then we have the registers. The registers are small, fast memory locations inside the CPU that hold data and instructions temporarily. What that means? That means, for example, that you are going to compare 15 with the result of 7 times 2. So this is data and this is data. This data is going to be stored temporarily in the CPU. And this is an execute instruction. Okay, you are going to multiply those numbers. So that instruction about multiply those numbers is an instruction. And that instruction is going to be temporarily stored in the CPU. Then you are going to compare the 15 with the multiplication result. That is another instruction. It's going to be stored temporarily in the CPU. That process is called register. Okay, I hope so. Let's continue. Now, the cycle of the CPU called the fetch, decode, execute cycle. So I'm going to start explaining that, but let me delete my board. So here and here. Okie dokie. Okay, fetch. Get the next instruction from memory. So remember this part. So we have the CPU, we have here the memory. Okay. So in the memory, we have lots of information. So the CPU get the information that is going to be performed. Okay. So that is called fetch. Okay. Decode, work out what the instruction means. So let's suppose that here in the memory we have this operation. So the CPU get the instruction, this instruction, and decode the instruction that is to be understood by the CPU. So I'm going to give you an example. Let's suppose that let's suppose our class is in Spanish, okay? And let's suppose that someone arrives to our class. Nobody knows English. Nobody knows English. And let's suppose that one English teacher arrives to our classroom and starts speaking just in English. So one of you knows a lot of English, just one student, and that student starts decoding and, in another words, starts translating what the English teacher is telling us. So that is the process of the code. Okay, so the CPU transformed the information in a language that the CPU understood that instruction. Okay, so we have fetch, the code, work out what instruction means, and execute. So carry out the instruction. That means that start executing the instruction. Okay, next one. Now, what is a microprocessor? Okay, a microprocessor is a small single chip that contains a CPU or parts of it, memory in some cases, other necessary components, and the microprocessor is an example of an integrated circuit, the IC, which means many electronic circuits are built into one tiny chip. So let me show you here. Okay, so we have something that is called microprocessor. So that means that we have, let's suppose that this is a CPU, and inside this one, we can have another tiny microprocessors. Okay, so small processors inside another one. Okay, it's a small single chip that contains this. So here you have CPU, memory, and another parts if that is necessary. Okay, so key facts about microprocessor. You can find microprocessor in many devices. Today is not only in the computers. Today you have it in your smartwatches, you have it in your cell phones, you have in your television, you have in your microwave, you have in your freezer, and many more devices, technology devices that you have. Those microprocessors handle different tasks, but specific tasks. For example, if you have a microwave, the microprocessor that the microwave has executes a specific task. Okay, and those are designed to make devices to work an automatic way or smart devices. Okay, let's continue. Now, difference between a CPU and microprocessor. The CPU is a part of a computer system. Okay, the microprocessor can be the entire processing unit of a small device. The CPU handles full computing tasks. The microprocessor often handles specific control tasks. The CPU usually in desktop and laptop computers, and the microprocessor is found in everyday devices like TVs, cameras, smartwatches. For example, in this moment, I am using Apple Pencil. So here inside this one, you have microprocessors and more. So CPU is something that the computer has and is for many tasks. A microprocessor is a tiny thing that is used for specific task. For example, the computer is not the same that a smartwatch. Okay, the smartwatch is done for executing specific activities, not only showing the hour, for example, showing your heart signals, your cell phone notifications, and for example, countdown or a chronometer. Okay, so those are specific tasks, and the smartwatch can't not do activities like the computer does. Okay, so that is the difference. A CPU is a huge system, and a microprocessor is done just for a specific task. Okay, now this is the part that is going to be a little bit more difficult here. That is called the von Neumann architecture. Okay, so please sit down and pay attention. Okay, if you don't understand something here, pause the video, rewind the video and watch the video again and again and again. Okay, so the von Neumann architecture is a model for the instruction and the data inside a computer. Okay, and it's all the way that the instruction and the data is stored in the memory. Okay, almost all modern computers are based on this architecture. Okay, the principal idea, the key idea. One single memory holds both the program instruction and the data, okay, that the programs work with. Okay, so I'm going to give you an example. Okay, so that means that here, let's suppose that this is a computer. The computer, you execute instructions, is not with double T, sorry. That instruction is stored in the computer, and you have data that obviously is stored in the same computer, and the instruction and the data is executed by the computer. Okay, so both information, even data and the instruction, is stored in the computer. Okay, so let me put something here like this. Okay, so the purpose of the components in a von Neumann CPU. Remember, CPU is central processing unit. So one of the components of the CPU is this one that you see, and we talked a little bit a few moments ago, is the ALU. Okay, so the components in a von Neumann CPU, the ALU, the arithmetic logic unit. So as I told you, this is the one that performs math operations and logical operations. Okay, so we have the control unit. In the control unit is the operations that the CPU is going to perform. So the control unit fetch the information, the data, the operations, decodes that information, and execute that that information. Okay, and obviously control the flow of data. What is the flow of data? Is the way that the data is going to take. Okay, for example, let's suppose that here we have the ALU, and let's suppose that here we have the control unit. Okay, and let's suppose that here we have the memory. Okay, so the control unit has the instructions in order. So the first instruction says that we need to multiply 7 times 2. So the control unit comes to the memory, fetch the information. So fetch the 7, the 2, and the operation. and gives that information to the ALU to be performed, right? And let's suppose that that information is going to be stored in our hard drive. So this information is going to be stored. Or maybe the information is going to be displayed in a screen. Okay, that is that the control unit does fetch the information, decode the information, execute the information, and is in charge of the flow of data. Every single arrow that you have here is the data flow, and that is managed by the control unit. Okay, let's continue to the next one. The second component in the von Neumann architecture is the registers. So the registers are small fast memory locations inside the CPU that hold important data temporarily. Okay, so those are the registers that we have. So we have the program counter. The program counter store the address of the next instruction to be executed. What that means? So let me show you. So the PC program counter. Let's suppose that the program counter has a list. Let's talk about a party that you are going to control who is getting inside the party and who is not going to get inside the party. So you are the program counter. So you say, so please, to get inside the party, you are going to make a line. So you are the first in the line, so get inside. You are the second in the line, so you get inside. So that means that the program counter is the one that is going to be the order of the instructions to be executed. Okay, that is the purpose of the program counter. Um, but here it said store the address of the next instructions. So what that means that here we have the RAM memory, for example, and inside the RAM memory, we have located the instructions. So let's suppose that the first instruction is going to be located in, this is an address inside the memory RAM. If you notice, this address is given in hexadecimal numbers. Okay, so the program counter has the list of all the instructions, but here we have the address of the instruction. So here we have 0x to the 4. This is just an example. So this is the address of the instructions. I'm going to give you an example. Let's suppose that you are in a tournament, a rally. Let's suppose that you are in a rally do you remember the previous year when you were in ninth grade about um, Julian Martinez when he do exercises with you about math? That, for example, he said, okay, you have an instruction to be executed in the CCA. So you move faster to the CCA, and there you have the instruction that you need to perform to continue to another part. So let's suppose that this list of places that Mr. Julian gives you is the program counter. So the first instructions is in the CCA. The second instruction is in the Agora. The third instructions is in the restaurant. The fourth instruction is in the soccer field, for example. That is the program counter, okay? Is the one that had all the addresses of all the instructions. Now, the memory address register. So the memory address register is the one that has the addresses of the memory location. Okay, so let me show you here. We have the program counter and we have the memory address register. Okay, so here and here. So as I told you, the program counter has a store that one instruction is in the CCA. Okay, so here in the MAR, that is called the memory address register, in the part that is called CCA, let's suppose that here you have this information. Okay, so in the program counter, you don't have the instruction. The instruction has it, the memory address register, but using an address. So let's suppose that this is the address. So that means that if this one is going to be executed, so we come here to this address, and here we have the operation that we are going to perform. Okay, so um, we have the MDR, the memory data register. It says that holds the actual data that is being transferred to or from memory. Let me explain this. So, the same. We have the CCA address. In the CCA address, okay, we are reading this information. This is a D. Okay, we are reading the information in this address. What is the information? This one. So that means that the MDR, let me show you what once again, what is that? Memory data register is the data. Which data? This data. One thing is the address. Let me try to explain this in a different way. Una cosa es que ustedes tengan la dirección de donde está la información. Entonces, en el CCA van a encontrar la instrucción. Ustedes se van al CCA y dentro del CCA van a encontrar una hoja que dice que tienen que multiplicar 7 por 2. Ese 7 por 2 es la información como tal. En este caso, es una información que ustedes están leyendo, el 7 por 2. ¿Listo? Entonces, ese 7 por 2 está en el MDR, que es el Memory Data Register. ¿Listo? Es una información que están leyendo de la memoria, pero recibieron la instrucción de que ustedes tienen que multiplicar ese 7 por 2 y su resultado, que es el 14, lo deben llevar al Ágora. El Ágora es otra dirección. Lo voy a escribir acá. Ágora. Es otra dirección. Entonces ustedes se van corriendo al Ágora a llevar el 14. Entonces ese 14 ustedes ya no lo están leyendo, lo están escribiendo y lo están escribiendo en la dirección Ágora. ¿Listo? So that was just a simple example in Spanish. That means that here holds the actual data that is being transferred to or from memory. When you are reading from memory is, for example, the 7 times 2. You are reading from the CCA and you are getting the 14 to the Agora. So you are writing. So you are transferring to, no from, by to. Lo explico así. Transfer to quiere decir que ustedes hicieron la multiplicación del 7 por 2 y el 14 lo llevan al Ágora. Ahí están transfiriendo al Ágora. Y cuando les dijeron, vayan al CCA por el 7 por 2, ahí están transferring from, es decir, que están leyendo. ¿Listo? Entonces, cuando usted dice transferring from, es que están leyendo. Y transferring to es que están escribiendo. Right? Okie dokie. Now we have the current instruction register, the CIR. This one holds the current instruction that it's being executed. Okay, so let me show you here once again. But let me try to draw this a little bit better. Okay, we have our counter program, or program counter, sorry, program counter. So remember that in the program counter, you have the addresses, the address where you find the information. So let's suppose that here we have CCA. So we have the memory address register. And here in the CCA, we have the multiplication 7 times 2. Okay? Okie dokie. Now, the MDR. Let's suppose that here we have the MDR. MDR. This one holds the information that is transferred to or transferred from. So if you receive the instruction to go to the CCA to get the instruction that you have there, that means that you are getting this 7 times 2, you are transferring to the MDR. So you have the information here. Okay. And we have the CIR. So here we have the CER. What is the instruction here? That you are going to multiply 7 times 2. So that means that this is the current instruction that is performed in this moment, that multiplication. So when you execute the multiplications, obviously the result here is 14. And this one, you have the instruction that you are going to take that 14 to the Agora. And here you have the 14 in the MDR that is going to be transferred to, not transfer from. This is transfer from, and in this way is transferred to. So that means that here you are going to have the 14. Okay? So I really hope that you are understanding. And the accumulator, that is the ACC, stores the result of calculation performed from the ALU. So that means that here you are doing this multiplication. This is the instruction that you are executing here. And this is going to be executed by the ALU. So remember that the ALU is called the arithmetic logic unit, is the one that is going to execute all the math operation and the logic operations. So the ALU is going to perform the multiplication. And the result, sorry, and the result of that multiplication is going to be stored in the ACC. Okay? So this 14 is stored here, the accumulator. Okay? So I really hope that this it's being clear for you. That is the reason that I told you that this is the hardest topic here. Now, all those information that I'm showing you here, look all the arrows. These arrows, this another arrow, this arrow, this arrow, and this arrow. So that means the information travels to one part to another part. And for example, if you want to travel from your home to the school, you need to do, you need to take a school route, or maybe you go in your father's car, or maybe you take an Uber or a taxi. So that transportation is called buses. Okay, so this is what we are going to start talking about. Buses. Bus is a pathway that transfers data between components inside the computer. Okay, so let me show you here. So buses. So let's suppose that you have your program counter, and here you have an address, for example, the CCA. Okay, then you have the memory address register, and here you have the CCA, and in the CCA you have this instruction. Okay, and you have, let me get back once again here. Then we have the seer, and this one is that has the instruction that is going to be performed. The instruction is the multiplication of 7 times 2, and this multiplication is going to be performed by the ALU. So here we have 7 by 2, or times 2, and in the ACCE we have the result that is 14. So if you notice, this information is going to move up, and we have the MDR. So all this information needs to move between these components to be performed. So this is an arrow, another arrow, another arrow, another arrow, another arrow. So that means that the information is traveling in all the computer elements. So that information travels by using buses, and we have three buses: address bus, data bus, and control bus. So what is the address bus? Address bus carries the address of where data should go or come from in memory in just one direction. Okay, so here we have this. So let me, I'm going to delete all the arrows. So that means that if, for example, we have the program counter has the address of the operation. So this information is moving using the address bus. Okay, so let me try to put in here. Is using the address. That means that in the address bus, the only information that is going to travel are the address that we have in our memory. Okay, so I'm going to give you an example. The same example. Están en las Olimpiadas de Matemáticas y los pusieron a correr diciendo, tome, aquí está donde usted encuentra la primera pista. Y usted coge el papel y en la primera pista ve el CCA. Usted sale corriendo para el CCA porque esa es la dirección donde está almacenada la primera instrucción. Ahí usted está usando un databus. ¿Por qué? Porque ahí solamente va la dirección donde usted encuentra la información. Y aquí dice que es usada en una sola dirección. ¿Ok? So, if you remember our previous video that we have data transmission, this is a video, this is no the here, data transmission. In data transmission, we have this part. Let me show you simplex. This one that is called simplex. Remember that simplex information travels just in one direction. So This is what we have here. So one direction from here to here. And if you want to move this part, let's suppose that from here to here, you don't use, let me explain this. The data bus on all the buses here has a lot of threads, hilos, tiene muchos hilos. Y en cada hilo viaja información en una sola dirección. Entonces, digamos que aquí se va para allá, solo para allá. Y si usted lo quiere regresar, digamos que se va por este lado. Just in one direction. Okay? One direction is the data bus. Let's continue. No, the address bus, sorry, the address bars. Why? Because you are moving just to the direction. Se está moviendo solo en las direcciones. Vaya al CCA, que ya está la primera instrucción. Usted se va para el CCA. In. Then we have the data bus. Carries the actual data being transferred between the CPU and memory or IO devices. Two directions. In two directions, we have this part that is called a half duplex. Okay, two directions, but not at the same time. So what that means, that for example, you receive this information. Tienes que ir al CCA, que allá está la primera pista. Ahí vas por el address bus, te vas al CCA. Y en el CCA te dan el 7x2 para que tú lo resuelvas y lo lleves al Ágora. Ya no estás llevando dos cosas, una nueva dirección que va en el address bus y llevas el 7x2 igual a 14, que sería el data bus. So the actual data that you are going to transfer from the CCA to the Agora, okay? And the control bus carries control signals to coordinate operations like read, write, and stop between components. So what that means? The control bus, okay, is like this one. Okay, you are going to take the information that you get in the CCA. So you go to the CCA. Okay, then you are going to operate the information 7 times 2, and you are going to take that result to the Agora. Okay, it's like the policía de tránsito, que dice, empiezas, pasas tú, después pasas tú, después pasas tú, después pasas tú. Okay, is the one that coordinates the operations. Like read what is that you are going to go to the CCA for the information. Right? That you are going to go to the Agora to take the result of the multiplication. Okay? I hope that is clear for you. Now, how do they all work together? So the PC program counter tells the CPU where the next instruction is. Is the same example. So the program counter, let's suppose that is Mr. Julian Martinez, and Julian Martinez tells you that the first instruction is in the CCA. So you move to the CCA. The MRA, memory address register. Take the address from the PC to locate the instruction in memory. Entonces, toman la instrucción del program counter, es decir, del profesor, y les dicen, tienen que ir al CCA. Okay? And remember, all the instructions, all the information is stored in memory. Okay? Then the MDR. Do you remember what is the MDR? No? Memory data register. So the memory data register fetch the instruction from memory. So that means that the instruction is that you are going to multiply 7 times 2. Okay, now the instruction moves to the CIR to be decoded and execute. The CER is the current instruction register. So you have the instruction that is 7 times 2 So let's suppose that you don't understand that. So you are going to translate it to decode it. Oh, we have to make a multiplication. That is decode, then execute. Okay. And if calculation are needed, in this case is needed because you are going to multiply 7 times 2. So the allow does the work. And the result goes to the ACC. And buses carry all necessary data and control signals around the system. So that means, van a multiplicar 7 por 2. Ah, 7 por 2 se lo dan al que sabe matemáticas, él multiplica. Esa es la ALU. Y él cuando le da el resultado se la da a alguien muy responsable que la guarda. Ese va a ser el ACC, ¿ok? El acumulador. Y los buses llevan toda la información necesaria y los controles. Es decir, uy, lleve esto allá, vaya allá, tome esto de allá, escriba eso allá, pero en orden. Eso es lo que hacen los buses, el control bus, ¿ok? Okie dokie, we just arrived to the half of the presentation. So what is the fetch, decode, execute cycle? So the FDE cycle is the process that the CPU follows to run a program. Every single instruction a computer carries out goes through this cycle over and over, millions of times per second. So this is how the computer fetch the information, decodes the information, and execute the instructions stored in memory. Okay. Step by step process. Purpose: get the next instruction from memory into the computer. Okay. So remember, fetch is when Mr. Julian tells you that you need to go to the CCA for the first instruction. So you fetch. So you go to the CCA, you decode. Why? Because you receive the information, and if the paper says they're going to move, you have just 7x2. So you need to decode that. And when you decode it, you understood that you need to multiply 7 times 2. Then you execute the multiplication. And this is all the time that the computer does. Okay. So step by step, you have here. Okay. So the action, the program counter holds the address of the next instruction. That is what I told you. Mr. Julian tells you that you need to go to the CCA for the instruction. That address is copied to the memory address register. So you put in your mind that you need to go to the CCA. That is the memory address register. Then the address is sent via the address bus to the RAM. So that means that you in your memory have the address of the place that you need to go to. Okay? Then the instruction stored at that address is fetched from RAM and copied into the memory data register. So that means that you have in your mind, in any part of your mind, the instruction, and you have the instruction. What is the instruction? That you need to go to the CCA, you get a piece of paper with the instruction. And the instruction says that you are going to multiply 7 by 2. That is executed by the current instruction register, the CIR. Then the PC is incremented by 1, ready for the next instruction. What that means. Instrucción número 1. Tiene que ir al CCA, recoge un papel, ejecuta la acción del papel, lleva esa instrucción al Ágora y allá usted va a recibir la siguiente instrucción. ¿Ok? So the PC, the program counter, is going to give you the order of the instructions that you are going to start performing. Okay? I hope so. Then we have the second stage, that is decode. In the decode, you have the control unit. So the control unit reads the instruction in the CIR. Okay? So the control unit es cuando usted le da el papelito al duro en las multiplicaciones y le dice, esto es lo que hay que hacer. Entonces lee la instrucción. Ah, hay que multiplicar 7 por 2. Ahí es cuando hace el decode. Okay. So you need to, you understand that you are going to multiply. That is the calculation or the operation that you are going to do or execute, and where that data needs to go to. Entonces, toman el 7 por 2, hacen la operación y la llevan al Ágora. ¿Ok? The instruction needs data. The control unit will fetch the necessary data from the memory using the same fetch process. Okay, so this is the process. You have the control unit, read the instructions. Where the instruction is? In the memory address register. Oh, the instruction says that we have to go to the CCA. Okay, let's go. And in the CCA, you have this instruction. You need to multiply 7 times 2. Okay. Okay, dokie. Then you have execute. Okay, so first fetch. So fetch means that you are going to go to the CC8 for the instruction. You got the instruction, you execute the instruction. Now you decode the instruction to understand what you need to do. Then you execute. Here, if any calculation is needed, the ALU is the one that is going to perform the calculations. The result of the calculation is going to be stored in the ACC, the accumulator. Okay. Now, the data, if the data movement instruction, the data is moved between registers or memory. What that means that you are going to move this. Okay, we need to get the instruction that is 7 times 2. We need to calculate that. You have a let me see. Something happens with my microphone. No, I think it's working. Oh. We have almost an hour. So I hope this is recording. I am not wasting my time here. Okay, so the data needs to move. Okay, so remember that every information that you work or you use in the computer, always the information is moved to the memory and to the registers, to any place that the information needs to go. And the information moves about using the buses. Okay, so some information is in the address bus. Which information moves in the address bus? Just the information is located. The database has the information that is going to be used in our executions. And the control bus controls the order of the instructions. Okay, now the results can be output. That means that is going to be shown using the screen, or need to be stored for in further instructions. That means that, for example, you receive the number 15. Okay, then you receive the 7 times 2, and you are going to save those information to compare if 15 is equals to the result of the multiplication 7 times 2. Okay, then the cycle repeats, starting always from fetch. Okay, okay, let's continue. How the components work together. So here you have the information. Okay, so the PC tracks the next instructions. The MAR holds the memory address to fetch from. The MDR holds data coming from or going to the memory. The CIR stores the current instruction to decode and execute. The control unit controls the entire process and decodes instructions. The ALU handles calculations and logic. The ACC holds the result of calculations, and the buses are used to move the address or move the data or control signals. Okay, so this is kind of diagram in the way that this is performed. Okay, first PC, then MAR, then RAM, then MDR, then SIR, then Q, then ALU, then ACC. In addition, the buses move the data, okay, and you start over again. PC, MAR, RAM, and etc. Okay, so what affects the performance of a CPU? So the speed and power of a CPU are influenced by several key features. Mainly, what is core? Oh, sorry, what is happening here? Okay, the core, the cache, and the clock speed. The core. What is a core? The core is like a mini CPU inside the main CPU. Each core can fetch the code and execute independently. Okay. So remember that I told you the cores is the way that the CPU is divided in, and every single division you have brains, for saying like this. So let me explain it in this. Let's suppose this is a core. This is the CPU that has one core. Possibly you are going to have another CPU. This is the same CPU, but with two cores. That means that this is going to be faster than the first one. This is dual core. And for example, you have this one, and here you have a core, 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 core. This is faster than this one. That means this is a quad core. And let's suppose you have something like this. Okay? So here you have a core, 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 core. That one is an octa-core. That means that is faster than this one. So as much cores you have, the process is going to be executed faster. Now, the cache, remember that the cache is an space of memory, okay, inside the CPU that stores frequently used data and instructions. So the CPU doesn't have to get the information from the RAM. Remember that reading the RAM is slower than reading the cache, okay? Okay, how the cache affects performance? The larger cache, more data CPU can quick access. More cache reduces waiting time, making the CPU faster. And we have some types of cache, but this is just for extra knowledge. Because I know that in IGCSE you are not going to be assessed about this. L1 is smaller and faster, L2 larger but a bit slower, L3 even larger but slower than L1 and L2. This is just extra information. You are not going to be assessed in these slow topics. Clock speed. What is the clock speed? The clock speed is an internal signal that tells the CPU when to move the next step for the fetch decode execute cycle. So how does the clock speed affect the performance? So the clock speed is measured in gigahertz. 1 gigahertz means that you are going to the CPU is going to perform 1 billion cycles per second. What cycle means? Fetch, decode, execute. Okay. As higher you have your clock speed, you are going to read more more instructions. Okay. Next one. This is just a summary table. Okay. Yeah, I'm going to move. So, I don't know why I'm thinking that this is not recording. I hope this is recording. So, what is an instruction set? An instruction set is a complete list of all the basic commands that a specific CPU can understand and execute. These commands are written in matching code, that means in binary, and tell the CPU exactly what to do. The purpose of an instruction set is to define the tasks that the CPU is capable of performing. It gives the CPU step-by-step instructions to complete operations. Let me give you an example here. And I think with this example, you are going to understand what is meant by instruction set. Okay. So, instruction set is just a list of instructions that is going to be executed. So first one, go to the CCA, then execute the multiplication of 7 times 2. Give the result of that multiplication in the Agora. Now you are going to execute more and more instructions. That is the instruction set. It's a list of instructions that the CPU is going to execute. Okay. Next one. Why is this important? If you don't have a set of instructions, you don't know what you have to do. It's the same with the computer. If the computer doesn't have an instruction set, the computer is not going to be able to perform any task. Okay, so every program when is running is broken down into these basic instructions. Okay, so different CPUs have different instruction sets. So software is often designed to match the CPU. So let's suppose in the image that I gave you here that you have, for example, different CPUs. So let's suppose that here we have PowerPoint, and in this one, in this CPU is going to be in charge just for opening the PowerPoint presentation, and this one is going to perform all the modifications that we are going to do. And both makes that PowerPoint works. Okay. Okay, this is an example of instruction and instruction set simplified. So matching code 0001. What it does, add two numbers. 0010, what it does, subtract two numbers. 0011, move data from memory to a register. This is just an example, okay? So you have the instruction in matching code that means in binary, and obviously the computer is going to decode that information to understand what it's supposed to do, okay? Key points, instruction set they are in binary. Each um, CPU design has its own instruction set. So every single CPU has an instruction set. All programs and applications are eventually translated to instruction set from this set for the CPU to execute. The fetch, decode, execute cycle uses the instruction set to know what to do with each instruction. So everything that I talked to you about this part, all this needs an instruction set to know all the processes that need to be executed. Okay, this one. Um, this is too short. What is this? Is something different. Embed system. An embed system is 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 I'm just watching if the microphone is recording. An embed system is used to perform a dedicated function. For example, domestic appliances, cars, security system, lighting systems, or vending machines. This difference this is different to a general purpose of a computer that is performed to execute many executions. For example, the computer is not an embedded system. Computer is a computer. In the computer you can play. In the computer you can study. In the computer you can do homeworks. In the computer you can read. In the computer you can listen to music. And many tasks. When we are talking about embedded system, that means that is something for specific task. Okay, so I'm going to give you an example. At school, we have a kind of embed system about the how do you say that? Digamos el sistema contra incendios. Sistema contra incendios tiene unos dispositivos que son los encargados de estar leyendo el ambiente para ver si hay humo y cierta cantidad de humo. Cuando hay cierta cantidad de humo, empieza a enviar, dice, uy, no, miren, esto es demasiado humo, quiere decir que hay un incendio. ¿Qué hace? Enciende las alarmas. Eso es un embed system. Es algo que está hecho para actividades o tareas específicas. Por ejemplo, otro, un sistema de irrigación de plantas. ¿Sí? El sistema de irrigación de plantas está leyendo que la humedad en la tierra es la suficiente para que la planta se pueda hidratar, por decirlo de cierta manera. Si ese nivel de humedad está bajo, quiere decir que les falta agua. Entonces manda una señal para que se encienda el sistema de irrigación y eso es lo que va a hacer que empiece a caer agua para las plantas. Eso es un embed system. Okay, so an embed system is a combination of hardware and software designed to do one specific task inside a larger system. For example, in the irrigation system, you have a sensor of sensor de humedad. You have the processor that is going to read the information that the sensor is reading, compare the information. The humidity is not enough. Is got to send an information to the actuator. That the actuator is the part that is going to put water on the plants. Okay, so we have sensors, CPU or microprocessors, and actuators. Okay, the purpose of an embed systems to control and manage a specific tasks, as I told you. Okay, they make devices smart by allowing them to to process data, respond to inputs, and carry out actions without human involvement. Okay, so this is what I already told you. And characteristic of embedded systems: dedicated functions, reliable, efficient, real time, small size, are are stored in ROM. Okay, so dedicated function performs one specific task. Reliable, designs to work continuously without errors. Efficient, often optimized to use low power and small amounts of memory. Real time, sounds responds instantly to inputs. For example, the airbags of the car. Or, for example, the example that I gave you. If the humedad is not enough, it's going to start putting water on the plants. Okay. Usually, compact of fits inside the device, and the instructions firmware are usually stored in on room in the read-only memory. Okay. And examples: washing machines, car, home alarm, microwave, smart lighting, and vending machine. Okay, so guys, I know that this video is too long, but I try to be so clear for you to understand this. So I hope you find this video helpful. If you have any question, let me know it. And thank you. Bye bye.